What if a forklift could lift not only boxes, but also itself? Introducing the forklift robot. The goal is to design a forklift cargo crate robot that can use its dual fork to solve puzzles by moving boxes. With a design in place, we start with a threaded rod, gear, and bearing to prototype a lifting mechanism. The motor is wired with a double-pole double-throw switch for reversibility. The box lid prevents the platform from spinning. It rides with the nut and can lift 2 motors. Anticipating the need for greater efficiency to lift the robot's weight, we got a lead screw. Much smoother. With the lifting mechanism prototyped, let's work on the fork. It has a double rack and is strengthened by rods. The blocks will allow boxes to move onto the fork. The fork will rest on a platform that can move vertically and control the fork's horizontal position with a motor. Bearings will allow the rack to move smoothly despite the load of the robot. With the motor, the pinion gears on either side engage with the racks to move the fork. The felt will help cushion the platform when it reaches its maximum height. To prevent the motor from popping up, we'll use zip ties in these table-sawed grooves. This high-torque motor with a gearbox will drive the lead screw. The robot will have tank drive. 2 belts will be controlled independently. Drive away! For ease of assembly, we made the wheel holders have through holes. It is finally time to print the frame. Unfortunately, a few layers were misaligned, resulting in a bumpy texture and a crack. Magnets will hold the detachable side panels in place. It is time to make the box drivable. The platform moves up and down the walls using ball bearings that ride in grooves on either side of the box. The lead screw can now be added, the fork inserted, and the motor and gear installed. The single lead screw is unbalanced when the fork is asymmetrical or carrying a box, a problem for later. Onward with the construction. Moment of truth. Surprisingly, it works on the first try. Up it goes. Now for the real test. Can it lift itself up? We had hoped printing all these gears would solve the problem of the motor not always engaging with the racks. But with the need for stability, it is time to redesign the platform and drill some holes. Whoops! The drilling almost bored a hole straight through the platform. Behold the new platform design that rides on 2 lead screws. This free spinning gear will connect the lead screws. The top panel holds the shafts in place. The platform moves vertically, and the fork slides back and forth. To control the robot, this receiver pairs with the controller's 4-channel transmitter to operate 4 motors in both directions. The maximum load is 6 volts, equivalent to 4 AA batteries connected in series. After turning on the controller, the receiver is turned on to pair them. The side panel will be held in place by magnets. The robot is ready, or so it seemed. A string of problems emerged. The gear was spinning on the motor shaft due to the high stress, causing the lifting mechanism to stop working. Taking off the top panel broke multiple supports. The second lead screw was cut too short. Fortunately, adding a spacer is an easy fix. The crack from the print failure widened substantially. To seal the gaps, we experimented with wood filler. After sanding off the excess, it looks much better. Next, the gear and its holder. The matte brown filament ran out, so the print was finished in red. This square is printed with 100% solid internal infill to maximize lifespan. After replacing the spur gear in its holder, the fork would only move up on one side. The gears connecting the lead screws were slipping. Larger gears came to the rescue. With the robot fixed, let's try a simple puzzle. To solve this puzzle, the robot needs to climb atop the far box. This is the robot operating in real time. Unfortunately, as the receiver operates on 6 volts instead of the 9 volts we tested with, the motor torque and speed have been reduced substantially. The robot has surmounted the stacked boxes. With the robot ready, it is time for the puzzle elements. This water-activated tape will smooth the box seams to prevent the fork from getting caught. Box 1 complete. Ramps will also serve as elements of the puzzle. Unfortunately, the wheels are not low enough, so the robot's box edges scrape on inclines. But a gentle lift helps the robot make it onto the ramp. Let's try it out with some game pieces. Next is the main structure. Part of the puzzle will involve lowering a drawbridge to cross a chasm. As with any heavy drawbridge, a counterweight is necessary to reduce the net torque. A few old batteries does the trick. A micro switch will control the drawbridge. When the button is held, the bridge opens. When it is released, the bridge closes again. Just as we are doing some preliminary testing prior to recording the robot completing the level, we find the drivetrain seemingly ruined, unable to turn in place and repeatedly slipping. Unable to quickly solve the issue, we disassemble it. The motors seem to lack the torque to rotate the belts in opposing directions. We try replacing the yellow TT motors with high torque micro motors, but even they lack sufficient torque. The next attempt involves wheel holders to lock everything down. The holes are printed to fit zip ties, the non-adhesive version of superglue. But despite it appearing to work well without a load, carrying the robot's weight is another story. Desperate to tighten everything down, we drill hole after hole to thread zip ties through. But the belt keeps slipping, and the motor's high torque has led it to spin freely in the wheel. Similarly to using rubber bands, adding high friction tape to the outside of the belt also does not work either, due to a lack of glue adhesion. We even try switching to 4-wheel drive, printing these wheels with fuzzy skin for extra grip. We wire them in series to maximize the torque output, compromising speed, but they lack sufficient turning capabilities and still are unable to climb ramps well. With the robot's base structure compromised and ideas for a more robust design, we decide to take the robot completely apart to add in new, longer belts to help with driving up ramps. Finally, we are back to building, with a reprinted box housing new wheel and motor mounts and zip tie holes. First are the lead screw holes, and next are the larger wheels and belts. Zip ties will secure the motors. And now we reverse the disassembly process. With the larger diameter wheels, these sleeves will elevate the robot when climbing and stabilize boxes. Trying to maximize voltage output to address the low torque, we fry 3 receivers and scorch the table, but we eventually settle on this 2-channel receiver that can handle 9 volts, despite it being rated for 6. Leaving the original controller to operate the fork. These improved fork sleeves also hide the unattractive seams of the original design. This fitting controller houses the tank drive transmitter. Time for a paint job. These buttons will press on the levers on the transmitter to control the robot. The antenna slides onto the turret of the tank. With both the tank drive and forklift transmitters ready, it is finally time for action. A bitter breeze bites the barren ocean's crest. Soundly sleep the sailors at day's rest. Aboard the pirate ship deck the relic lies. Elusive have you been to sneak unspied among the cargo crates crammed below. Exhausted batteries leave your actions slow. Fear of perishment elevates the mission's pressure. Will you return the sacred stolen treasure? This project began with trying to use receivers and transmitters. Some experimentation led to constructing a prototyped remote-controlled car. As we brainstormed ideas for what the robot might do, we used a modified syringe, coiled enamel wire, and neodymium magnets to make a solenoid launcher. We tested micromotors, envisioning a grappling hook launched by the solenoid that could hoist the robot, but we eventually settled on a forklift automaton, one that could lift both boxes and itself. One designed to blend into the other cargo crates in a ship heist narrative. From paper to cardboard, ideas for puzzles the robot could solve sprouted into being. From designing to printing, to prototyping and experimenting, to problem solving, we learned to print stronger motor connectors, to make snug fit connections less tight and permanent for when something inevitably fails, to not tamper with the 3D printer while in action, to use wood filler for plastic cracks, and to measure thrice and account for wear and tear. This project has been a massive undertaking and a valuable lesson in persistence. We hope you enjoyed venturing on this journey with us. Thank you for watching.